Welcome to this exploration of binary trees, one of the most fundamental data structures in computer science. A binary tree is a hierarchical data structure where each node has at most two children, referred to as left and right children. Binary trees are used in countless algorithms and applications due to their efficient structure. Let's understand the structure and terminology of binary trees. The topmost node is called the root. Nodes are connected in a parent-child relationship. Nodes with no children are called leaves, while nodes with at least one child are internal nodes. Some important properties of binary trees include the relationship between level and maximum number of nodes. At level L, the maximum number of nodes is 2 raised to power L. Also, the maximum height of a binary tree with n nodes is approximately logarithm base 2 of n. Binary trees come in several varieties. A full binary tree has nodes with either 0 or exactly 2 children. A complete binary tree has all levels filled except possibly the last level, which is filled from left to right. A perfect binary tree has all internal nodes with exactly 2 children and all leaves at the same level. A balanced binary tree has a height of order log n, making operations efficient. Understanding how to traverse a binary tree is fundamental. There are several common traversal methods: in order, pre-order, post-order, and level order. In in-order traversal, we visit the left subtree, then the root node, then the right subtree. This produces the nodes in sorted order for binary search trees. In pre-order traversal, we visit the root node first, then the left subtree, then the right subtree. This is useful for creating a copy of the tree or prefix expression. In post-order traversal, we visit the left subtree, then the right subtree, and finally the root node. This is useful for deletion operations and evaluating expressions. Binary trees have numerous applications in computer science. They're used to represent mathematical expressions, implement data compression algorithms like Huffman coding, create efficient priority queues with heap structures, and build decision trees for machine learning models.